things. It will help us with the lab for today. And it will also help you since our next exam is coming up a week from Thursday is when we're rolling with that one. So let us continue on here. We've been talking about sort of boiling point, melting point. So where we just did that one, I think. All right, so we are on to this one here. So take a moment or two. We want to know how many grams of ethylene glycol must be added to 1 kilogram of water. That gives a solution that boils at 105 degrees Celsius. And again, our KB in this case, since we are going to be using a KB, should be 0.512 degrees Celsius per molality. All right, so take a couple moments there and see what you come up with. Once again, our normal characters of carbon being 12.01, hydrogen 1.008, and oxygen being 16. So here we have some boiling point information. Okay, let's take a look. We want to know how many grams of ethylene glycol, which is our solute here, going to be added to water, which is our solvent. That is, again, how we know we should look up the KB there for water. We also know that water, which is the solvent here, has a boiling point of 100 degrees Celsius, a normal situation. In this case, we actually have a solution that boils at 105 degrees temperature. So we can think of our boiling point formula, which is our change of boiling point temperature equals our KB times our molality. Now, in this case, we ultimately want to figure out how many grams of our solute, and that is going to be actually tied up in our molality, which is the moles of solute over kilograms of solvent. So that's really where the moles of the solute is going to come from so that we can get to grams of the solute. So to do that, we're going to use the boiling point information here to help us do that. It is really important to note that this number right here is not the 105 number. We do need to use our relationship for the change in boiling point, which is actually the temperature of the solution minus the temperature of the solvent, where it normally boils. That means the change in boiling point temperature will actually be 105 minus 100 degrees Celsius, which is actually only 5 degrees Celsius that should go into here. Again, not where it boils, but actually the change in the boiling point temperature. That means we can solve for M, which would be the change in the boiling point temperature divided by the KB. That would give us 5 degrees Celsius divided by 0.512 degrees Celsius molality. The degrees Celsius will cancel. And once again, give us molality up on top when we divide it. And that gives us something like 9.77, we'll call it. And that would be moles of our solute divided by our kilogram of solvent, which in reality is our C2. We got there H6O2 is our solute. First off, any questions up to that point? Now we can use the other piece of information which they gave us, which is that we're taking a kilogram of the water, which is our solvent. So frankly, if we just multiply this by 1 kilogram, which is our solvent, which is the water, the kilograms of the solvent will cancel, and that will give us that we have basically 9.77 moles of C2H6O2 in this particular case. Now we are very much close to what we need, which is how many grams of that. So the last thing that we would need to do is a little molar mass action here. So that's going to be 2 times 12.01 plus we got there 6 hydrogens times 1.008. And lastly, a couple of oxygens at 16. Going to give us 6207 grams per mole. And we'll times that by 9.77. Means that we need roughly something. We need roughly 610 grams of C2H6O2 in this particular case. Any questions on that? So again, here we're using the boiling point information, kind of like what we did with the freezing point, to actually figure out some other aspects of what's going on with this particular solution. So a lot of these type of problems, sometimes you got to think of them almost like conversion type problems, units, and what will get you to ultimately what you're looking for and what you need to sort of solve. Any question on any of those steps there? Okay, let's try another one here. Hopefully they agree. Let's hope so. It's good. All right. All right, so here we want to actually calculate what is the boiling point temperature of a solution you made by dissolving 1 gram of glycerin and 54 grams of water. So once again, here our solvent being water and our doing boiling point, I believe. So we'll use our 0.512 degrees Celsius and molality, and our normal boiling point would obviously be 100 degrees Celsius. Again, we'll employ our formula here. In this case, we obviously looked up our boiling point constant. They did not give us the molality, so we do want to calculate it. So the molality here will be our moles of solute, kilograms of solvent. In this case, obviously, this is our solute, and the water here would be our solvent. So the kilograms of solvent, not too bad, 54 grams, just converting that into kilograms, so you can move some decimal over if you like. Should give you 0.054 or 0.0540 kilograms. For the moles, we need to calculate the molar mass of that. So that is 3 carbons at 12.01 plus, I think it's 8 hydrogens, 1.008. And we got 3 oxygens, I think it says. So the molar mass there is 9209. So we'll take our grams, 1 gram C3H8O3 using the molar mass would be 9209 grams per mole. And that gets us 0.0109 moles, which we could then divide by our kilograms of solvent, 0.0540 kilograms. Gets us a 0.201 for our molality, which is what we need there. So putting that into our equation, we end up with 0.512, which is our constant for water, and our 0.201 molality. They cancel, gives us a 0.512, 0.103, we'll call it degrees Celsius. That once again is not the boiling point of this solution, but that is the change in the boiling point temperature, which the change in the boiling point temperature would be the temperature of the solution minus the temperature of the solvent. So in this case, we got 0.103 degrees Celsius equals our temperature of our solution minus where water normally will boil, which is 100 degrees Celsius. We're going to add that to the other side, which gives us a whopping 100.1 degrees Celsius as where this solution would boil. So it'll elevate it a little bit, 0.1 degrees Celsius, basically above the normal boiling point of water. So in this case, we did have to calculate the molarity, which is again a common sort of situation. Any questions on any part of that there? Okay, so then let us continue on here. That's what we just did, I think. Perfect. That's the one we just did, so that's good. All right. The next thing we're going to talk about is actually osmotic pressure. And osmotic pressure occurs when we have a separation of a solution from a solvent by a semi-permeable membrane. So for example, you have a membrane in this sort of tube. And on one side, say we have salt water. And on the other side, say we have just water. The process of osmosis is the process where solvent molecules move from a lower concentration to a higher concentration. The little brackets mean concentration. So in an effort to sort of dilute down the other side, the solvent molecules will continue to kind of flow from the lower concentration to the higher concentration. And in our example here, if we have those two sides sort of separated here by a membrane in the middle, the water is lower in concentration as it obviously has nothing dissolved in it. Salt water is basically water with stuff dissolved in it, so it is more concentrated, has more particles. So the water will actually flow from the left-hand side through the membrane to the other side, and it will continue to flow to the saltwater side in an effort to dilute it down. It will continue to flow until it hits basically what is known as the osmotic pressure, which is sort of the atmospheric pressure, kind of pushing back down on it. At that point, what will happen is it will prevent basically the additional flow of solvent molecules across the membrane to the other side. It sort of puts a stop to it. Reverse osmosis is when you apply a pressure greater than the osmotic pressure to this side, and that pushes everything back the other way, where you have filters and stuff that grab all the stuff that you don't want, and you get kind of pure water on the other side. It's basically kind of the process of reverse osmosis. So we can actually calculate osmotic pressure by using this wonderful equation here. This is the osmotic pressure. And this equation is one where, frankly, you've seen before because it is PV equals nRT. So they use a funky symbol for P. So this is basically the ideal gas law. And since this is really the ideal gas law, normal rules apply. Our pressure does need to be in atmospheres. Our temperature needs to be in Kelvin. Our volume needs to be in liters. And it is the same gas constant that we use with the ideal gas law. So really, it's just ideal gas law. If you solve for the pressure, which is nRT over V, I think we talked about this maybe when we're doing some gas problems. That is N, which is moles over liters, which is the volume. That is the molarity, which is why it becomes the molarity here. And that leaves us just R and T left over. So that's how we get to sort of this part of it here. So really, this is just an ideal gas law problem, and you can use it to basically calculate the osmotic pressure in a situation. You could also use it to calculate other things, as we will see as well, like molar mass and stuff like that. Really the same way that we calculated molar mass when we did the ideal gas law in the gas chapter as well. So for example, if we wanted to know what the molar mass of a protein, that is 5.87 milligrams per 10 milliliters. It gives an osmotic pressure of 2.45 torr at 25 degrees Celsius. This is really just like we talked about in the gas chapter, the deal where you could use the molar mass equation, or as we talked about, you could just use the ideal gas law and sort of solve for units. So if we were to do this, we really do have the grams part off the bat here. Obviously, we do need to do a conversion to convert it from milligrams to grams. The rest of the information really is going to go into the ideal gas law. So PV equals nRT. We are missing moles, so we will solve for moles here, which would be PV over RT. We do have to do some conversions, obviously. Our volume is 10 milliliters, so we do have to convert that into liters. So that would get us 0.01 liters. Our pressure here is in torr, which means we do need to convert it into atmospheres. So that's going to be a 760 torr is an atmosphere. And that will get us 2.46 divided by 760. 0.00324 atmospheres. And lastly, like normal with gas laws, we do need to convert our temperature into Kelvin, and that should give us a 298 Kelvin. Obviously, we always have R, which is the same R that we used before. So really, we do have now everything that we need over here to solve for the moles. So to do that, we would take our moles would equal our pressure, which was converted to atmospheres, 0.00324 atmospheres. Our V, which was also converted to liters, 0.01 liters, divided by our R. And our temperature, which again converted to Kelvin here. Taking all those numbers into account will get us 0.01. A mole of 1.32 times 10 to the minus 6. So that is really the bottom part of what we need. So we still need to convert our grams into milligrams into grams. So that was 5.87 milligrams. And there are 1,000 milligrams in a gram. So we'll take 5.87 divided by 1,000. Gets us 0.00587 grams here. Any question on where any of those numbers came from? So in this case, we're again using sort of the gas law to get to moles. We have the grams given to us. So now to get to the molar mass, we are going to do a little division here of 0.00587 grams divided by our moles, 1.32 times 10 to the minus 6 moles. Going to get us a molar mass here of approximately 4,447 grams per mole, or maybe about 3 sig figs would be good. 445 grams per mole. So it is a protein, so it should have a pretty big molar mass in that case. Any questions on this? So really osmotic pressure, you can use the symbol, but it really is just the ideal gas law. And it's very similar to, again, as I mentioned, basically when we did the molar mass of gases and density of gases in the gas chapter. Any questions on that particular one there? All right, so questions on osmotic pressure, vapor pressure, boiling point, freezing point. So what I want to talk about next is those things, but up until this point, the solutes or the stuff that was dissolved in the solution, they've all been non-ionic. And when you have a non-ionic solute that you dissolve in the solution, it has a different effect on the colligative properties than if you actually dissolve something that is ionic. Remember that basically colligative properties are based on the number of particles that there are in the solution. So when you take something that is non-ionic and you dissolve it, you basically get something that's non-ionic dissolved. You basically get a 1-to-1 relationship in terms of you threw one particle in, you get one particle out. Basically, that's what happens. When you throw an ionic compound in as a solute, it is a little different. So for example, if I threw sodium chloride into a solution, that is actually going to break apart into sodium ions and chloride ions that are going to be floating around, which means for every one sodium chloride sort of unit that I toss in there, I'm actually getting 2 particles that are basically floating around. And that is going to affect the colligative properties a little bit more than if you took something that was non-ionic, where you basically only get 1 particle per 1 particle. Also would be different if I had something like calcium chloride that I threw in there. That would give me a calcium and 2 chlorides. which means I would basically get 3 particles for every 1 unit. So I'm getting like 3 times as much particles flowing around than I do in a non-ionic situation. So to account for that, that is what is known as the von Hoff factor, and that is what is sometimes abbreviated with an I. And the simple way to calculate the value of I for ionic compounds is pretty much what I just did here. For sodium chloride, the I value would equal 2 because you get 2 particles. For calcium chloride, the I value here would equal 3. And how these affect is pretty much all of the formulas we just used. You basically can incorporate the I value into those formulas. So you can take your change in freezing point, I is equal to Kf times M. You could also do it with your boiling point, I is Kb times M. You could also do it with your vapor pressure. And so forth. So we can incorporate the I or the von Hoff factor in when we are dealing with an ionic solute. So if you're dissolving something in a solution that's ionic, if you think about all the ones we did previous to this, they're all like carbons, hydrogens, and oxygens, non-metals sharing electrons, no ions that are going to go in there. So the reason that we really didn't need to use the von Hoff factor in all the ones that we did before is because with a non-ionic, I is basically equal to 1, right? Which means it doesn't really change the calculation or anything like that in that particular case. So how does that really affect, say, the boiling point or the freezing point of a solution? So for example, if we took a 1.5 molality sodium chloride solution versus a 1.5 molar calcium chloride solution versus our 1.5 molar non-ionic solute, like we'll just do our non-ionic. And we wanted to calculate the change in the freezing point temperature. So for our non-ionic, we would do our K, and these were all obviously in aqueous solutions. We would use our Kf value, which would be 1.86 times the molality times 1.5. That would give us a change in the freezing point of about 2.8 degrees Celsius. Now, when we get into a sodium chloride that's dissolved in there, that is going to give us, as we just talked about, an I value of 2, which means that the freezing point here would be I times 1.86 times our 1.5. And now basically we're going to end up with a change in freezing point of about 5.6 degrees Celsius. So because we have twice the amount of particles in there, it's actually going to lower the freezing point basically by 2 even more. And we see the same type of effect when we get to calcium chloride, which has an I value of about 3. Our change in freezing point would be 3 times our 1.86 times 1.5. And that gets us obviously here a freezing point temperature of about 8.4 degrees. So this is going to drop it even more. So you can see the more particles to get into that solution, the more in the way they get, the bigger effect that it has on things like freezing point and boiling point. Obviously, you can do the same type of calculation for the boiling point and so forth. You would see the same sort of effect. So if you are dealing with something that is ionic, you do need to incorporate the von Hoff factor in there, basically to the same equations, and you sort of like we just did there in these examples. Any questions on that there? All right, so this is non-electrolyte, which has a von Hoff factor of 1 and measured. We actually did experiments to measure the von Hoff factor. They are slightly off from what we would sort of expect based on the formulas, but you are safe in most calculations to really just do it from the formula like I just did a second ago. So obviously this gives us 2 ions. So we got a factor of 2. That gives us 2 ions. This guy gives us 3. This guy gives us 4. So I would equal 4. So in a calculated type problem, you can just use the formula to figure out how many particles it breaks apart into. And that will allow you to properly sort of calculate the effect on the boiling point. All right, so why don't you try this one? What is the measured von Hoff factor if you have a 0.05 molality calcium chloride solution and the freezing point is minus 0.27 degrees Celsius? Let's see what you come up with here. Okay, so let's take a look. So we're going to deal with the freezing point here. So our change in freezing point will equal I, our Kf, and our molality. Once again, this is ionic here. So that's why we do need to incorporate I, and plus that is what we're actually solving for in this particular case. It freezes at minus 0.27 degrees Celsius. Remember, once again, our change in freezing point is the temperature of the solvent where it freezes minus the temperature of the solution. That means in water normally will freeze at 0 degrees minus 0.27 degrees Celsius. That's going to give us our 0.27 degrees Celsius. And again, that is how we get rid of the negative here. So we will then solve for I, which would be the change in the freezing point temperature divided by Kf times M. And that would then be our 0.27 degrees Celsius, our 1.86 degrees Celsius times the molality. In this case, it gave us the molality of that solution, 0.05 M. And using that there, 0.27 divided by 1.86 divided by 0.05 gets us a I factor of about 2.9, which is fairly close to what we would expect if we just did it based off of the formula where this guy breaks apart into a calcium and 2 chlorides. That would be an expected I value of 3, which is very, very similar in that particular case. Any questions on that there? Yeah. Yeah. No, in this case, you can leave it at 2.9, and this was sort of a measured one, sort of experimental sort of value, and it is very close to what you would have in the formula. In a book type problem or a problem like that, you would just use the formula and use probably I as 3 if you were calculating something like the freezing point or boiling point or something like that. Other questions on that? Yeah. What's that? I would say in this case, you probably would want to leave it as 2.9 since all the numbers there are probably about 2 sig figs. So that probably would be what you would want to leave. It would probably be okay, I think, in that situation. But in this case, you probably want to leave it as 2.9 because you're looking for a more probably accurate sort of value since it's measured and more experimental rather than just kind of randomly from the equation. But definitely in a book problem, most of the time you will just take the formula, break it apart, and use that as your I value, and that's perfectly good to do in most cases. Yeah. Other questions on that there? All right, questions on boiling points, melting points, and boiling points, freezing points with ionic. So again, the major difference is you do need to incorporate the von Hoff factor. Fun with calculations now is if we take our boiling point one, maybe. I don't know how fun it will be, but we'll see. So let's say we're going to make some pasta, yeah? And we want to throw some salt into our pasta, right? Maybe throw a little sodium chloride or something, some salt in there. And if we took the molar mass of sodium chloride, 22.99 plus 35.45 gets you 58.44 grams per mole. So we throw some salt in there to, maybe make it boil a little higher or something like that. So let's just say randomly we pick, we'll get it maybe 2 degrees higher. So instead of your water boiling at 100 degrees Celsius, you want to cook your pasta at 102 degrees Celsius. So maybe you get done with your pasta a little bit quicker. So we're going to say our change in temperature here, and again, just randomly picking 2 degrees, sort of a modest change, would equal our I in this case, which would be 2, right? And our KB in this case would be our boiling point constant, and our M would be our molality. So dividing these guys to the other side, we take 2 divided by 2 and divided by 0.512, gives us a molality of about 1.95. And that is basically 1.95 moles of sodium chloride, say, per kilograms of water. So if we make, say, 4 quarts of water as we're boiling our pasta here, that's roughly 3,785 milliliters of water, which if we use the density of water of 1 gram per milliliter, that is roughly 3,785 grams of water, which if we divide it by 1,000 would be 3.785 kilograms of water, which obviously if you're boiling water, that is your solvent, as you throw just a little bit of salt in there. So if I take this and times it by 3.785 kilograms of my water in my pot that's boiling as I'm making my dinner tonight, we end up with a moles of about 7.39 moles, say, of sodium chloride, which if we multiply by the molar mass of sodium chloride, which is 5844 grams per mole, that's approximately about 432 grams of sodium chloride I would need to add to my pasta to get the temperature to go up about 2 degrees Celsius. How many grams are there in a pound? 453 grams in a pound. I'm assuming most don't toss a pound of salt in there as they are going to make their pasta. You maybe do a pinch of salt as you throw it in there. So probably your pinch of salt is raising that boiling point. Nothing basically, probably 0.01 degrees Celsius. But hey, it makes the pasta taste much better, I think, when you do it. So, it's more probably for flavoring than increasing the boiling point of your water to get it to, boil maybe at a higher temperature or something like that. And this sort of rough calculation, you can see you would need to put a ton of salt in there, probably to really get it to kind of increase a lot. All right, fun with calculations. All right, fun. All right, good. All right, let's finish this up here by skipping this example. All right, so let's talk about some properties of solution here to sort of finish out our talk of solutions and this chapter here. We talked a little bit earlier about a semi-permeable membrane, and that is really a membrane, kind of like cells. It allows certain things to pass through and other things to not pass through. And this really is sort of size exclusion, although a lot of times you can't really see it, but there's kind of holes and pores that allow certain size molecules to go through and maybe other ones not to go through because they are too big. Sort of how you filter out certain things as well. When we talk about colloids are much larger than solute particles in solution. Usually colloids are large molecules like proteins or groups of molecules or ions that are together. Colloids, though, are homogeneous, which means they do look the same throughout. They do not separate or settle out. They are small enough to pass through filters like filter paper when you funnel or filter out something, but they are too large to pass through sort of the holes on usually most semi-permeable membranes. Suspensions, on the other hand, are heterogeneous, and those are non-uniform sort of guys. They're different than solution and colloids. They are often large enough that you can see with your naked eye. So, for example, we took some water and threw some sand in there, right? You'd be able to see the sand in the water. That would be sort of a suspension. And as you know, if you try to filter your water and your sand through a filter paper, the sand is going to get caught on the filter paper. The water, which is a solution, will have no problem. Our liquid will have no problem basically to pass through the filter. Here's a blown up of a membrane, and again, there's really these holes or channels which obviously allows certain size molecules to pass through. Larger guys like this guy here is going to have a little bit of trouble, obviously, making it through to the other side. So our solution, colloids and suspensions, we can filter out solution of the colloids. It will go through filter paper, but again, our suspensions will be too big to pass through, and really our solution will be able to pass through something like a dialysis bag or something like that. If you ever use one, again, it has kind of pores on there that allows things to filter through. We talked a little bit about both of these things here, but once again, osmosis is that natural process where sort of a solution that has a lower concentration will flow into one of a higher concentration, really in an effort to sort of equalize the pressure on sort of both sides of the membrane. The osmotic pressure, as I mentioned before, prevents the flow of additional water molecules when it is reached. The greater the number of molecules that's dissolved in something, the greater the osmotic pressure something has. Water, pure water, has no osmotic pressure because, frankly, it's just water. There's nothing dissolved in it. Another way that sometimes you measure osmotic pressure is through what is sometimes referred to as osmolarity, and that is sometimes referred to as the osmol. And that is basically I times your molarity will equal your osmolarity. And so, for example, if you had a 4 molar sodium chloride solution versus a 4 molar calcium chloride solution, I here is our von Hoff factor, like we just saw and talked about. So we already know from our calculations here that I would equal 2 for our sodium chloride. I would equal 3 for our calcium chloride. So the osmolarity of sodium chloride in the solution would be 2 times 4, which would give us 8 osmolarity, while the same 4 molar solution of calcium chloride would give us an osmolarity of 3 times our 4 molar. And that will give us 12 osmolarity. We can see here, just based on the simple calculation, that calcium chloride obviously has a much higher osmotic pressure than sodium chloride, even if they have the same molarity, and it is really based on the number of particles that are dissolved in that particular solution. If you had a 4 molar non-ionic solution, it would be 4 times 1, which would give us a 4 osmolarity, which would obviously be less osmotic pressure that's based on it. Any questions on that there? All right. Now, there's really 3 ways to describe some solutions, and that is isotonic, hypotonic, and hypertonic. Isotonic solutions exert the same osmotic pressure as body fluids. Isotonic solutions are typically IV solutions, because if you're getting an IV solution, you probably don't want something that's going to screw up your cells. And basically what that means is, if we take the classic example for these things, which is a red blood cell, and you put that red blood cell into an isotonic solution, the osmotic pressure inside and outside of the cell are basically the same. The cell is acting really as a semi-permeable membrane, right, allowing things to flow in and out of the cell. And basically what you would have is equal flow kind of in and out of the cell, and everything would be happy in that case. By the way, what is considered an isotonic solution is 0.9% mass to volume sodium chloride solution, or sometimes referred to as a saline solution. Doesn't necessarily have to be sodium chloride, could be, potassium chloride, whatever it may be, and a 5% glucose solution. So those guys are really considered your isotonic sort of solutions. So if you have a solution that's either above or below that, it is going to be either a hypotonic or a hypertonic solution. If you have a hypotonic solution, hypo means less than. So it would actually be less concentrated outside of the cell than inside of the cell. So what would happen if you take your same poor red blood cell and you put it into a hypotonic solution, outside of the cell is actually less concentrated than inside the cell. That means outside of the cell is going to decide I need to flow into the cell in an effort to dilute it through osmosis, going to go from a lower concentration to a higher concentration. And as was just demonstrated there, that's going to cause the cell to swell and eventually burst, which is known as hemolysis there, as basically everybody rushes into the cell. It pops like a jelly donut and out it goes, which is probably, again, not a good thing if you put that into your body. Now, a hypertonic solution is opposite. Hyper means more than. So that means outside of the cell is going to be a higher concentration than inside the cell. So in that particular case, what's going to happen when we take our red blood cell and we put it into a hypertonic solution, outside the cell is more concentrated. Inside the cell decides I'm just going to release all my fluids there to try to dilute the outside of the cell in a process, again, through osmosis. The result of that is the cell is going to shrink and probably not survive very well, and that's what is known as crenation. Also not a great thing that's going to happen in that situation. Any questions on that there? So if there's our go. So this is isotonic. We have nice even flow. Hypertonic, everybody's flowing out of the cell, so it's going to shrink like a donut hole. And then we got our guys flowing in there in a hypotonic solution, going to pop like a jelly donut. So what will happen here to our famous red blood cell if I put it in a 5% sodium chloride solution, if I put it in a 2% glucose solution, if I put it in pure water, will it shrink? Will it explode? Will it be okay? Yes. So will it swell? Will it swell and burst? Will it shrink? Or will it be okay? Yeah. All right, take a moment and decide on each of those. All right, so let's take a look and decide here. So first off, we should remember, again, our isotonic solutions, 0.9% sodium chloride and 5% glucose. So that's really the ones we want to kind of compare to. So we'll start with the 5% sodium chloride. It is as simple as 5% is larger than 0.9%. So that would be a hypertonic solution, which means outside of the cell is going to be more concentrated than inside the cell. That means we're going to get the donut hole here, as all the water from the cell will rush out of the cell. It will start to shrink, go through crenation, and again, probably not so good. If we go with 2% glucose is less than 5%. So that means less than would be hypotonic. So this is the case where outside of the cell will be less concentrated inside the cell. So that is going to be this situation here. All the water is going to rush into the cell, going to cause it to swell and burst, which is known as hemolysis. And that also not so good. Any question on those two? Lastly here, pure water was still water, and it will kill you. Yes, water has no osmotic pressure, right? Which it means if it has no osmotic pressure, it probably is lower in pressure than the red blood cell. And that means that it is actually a hypotonic solution, and it will cause basically all the water to rush into your cells, which means water is not always good in all situations. This would perhaps be a situation where it's probably not so good if you were going to put a red blood cell in that particular case. Any questions on how to do that? Clearly, these numbers would probably be important to know. Yes. All right. So to finish up here, dialysis is a process similar to osmosis. It allows small molecules and ions to basically pass through. But again, it retains sort of larger particles like colloids. In the laboratory, sometimes people do use dialysis bags. For example, if you're working on a protein or something like that, and you want to put it into maybe a pH environment, You can put your protein into like a dialysis bag, put it into a buffered solution at a specific pH. It can allow it to sort of equilibrate to that particular pH, and then you can do your experiments like it would be done in its normal sort of environment. In our bodies, right, we dialyze ourselves there with our kidneys and all that kind of stuff, right, to get rid of products that we don't need. And obviously, if you have problems with that, you need a machine to help basically filter out, all those sort of impurities from your body that we sort of do naturally when everything's sort of functioning normally. All right. I think I'm out of slides. I feel like I'm out of slides. There it is.